Welcome back to Dr. Liu's VCE Chemistry channel. Today, we are breaking down fuel and heat of combustion from the 2025 NHT Chemistry exam. As I go through this, please feel free to correct me if you find any mistakes. All feedback from teachers, parents, and students is greatly appreciated. Referencing item 12 of the data book, and utilizing the nutritional breakdown of protein, fat, and carbohydrates per 100 g of biscuit, the total energy was calculated to be 1,603 kilojoules for 100 g. To create 250 mJ of energy, the theoretical mass of bioethanol required 30 mJ per kilogram, specific energy, and 100% efficiency, is 8.33 kilograms. However, allowing for the actual 25% efficiency, the mass needed is, resulting in approximately 33 kilograms of bioethanol. A calorimeter with a digital temperature probe was calibrated. The calorimeter was then used to measure the enthalpy of a chemical reaction. The graph below shows the 6 temperatures recorded in the first 5 minutes from when the reactants were mixed. While good lab practice, such as experimenting with standard laboratory conditions, doesn't directly improve the precision of the peak reading, the best way to reduce heat loss is by using a better insulator, like a bomb calorimeter, or ensuring the starting temperature is slightly below the final temperature of the surroundings. But option C specifically improves data quality. This changes the entire experiment by measuring a different value. It does not address the experimental technique flaw, low data frequency, that causes inaccuracy in reading the peak temperature of this reaction. This would severely worsen the accuracy. Waiting 10 minutes between readings would mean the temperature peak would be completely missed, and the recorded temperature would only show the final, much lower temperature after significant heat loss. Recording the temperature every 20 seconds is the best improvement because it increases the data density, making it more likely to capture the true maximum temperature before heat loss becomes significant. Since one octane molecule contains 8 carbon atoms, and according to the conservation of mass, 1 mole of octane produces 8 moles of carbon dioxide. Therefore, when 1.5 moles of octane is completely combusted, 12.0 moles of carbon dioxide is produced, which is equivalent to 528 grams, using the molar mass of 44 g per mole. The combustion of octane involves 2 simultaneous processes, breaking existing chemical bonds, which requires the system to absorb energy, and forming new chemical bonds, which causes the system to release energy. This reaction is classified as exothermic because the total energy absorbed during bond breaking is less than the total energy released during the formation of the new product bonds, water and carbon dioxide. The problem provides 2.0 moles of octane and 21.0 moles of oxygen, resulting in an oxygen-octane ratio of 10.5, which is less than the required 12.5 for complete combustion. This confirms incomplete combustion must have occurred. Given that no pure carbon is produced and no reactants remained, but the reaction is partially incomplete, the product formed in addition to the complete combustion products, water and carbon dioxide, must be carbon monoxide. The energy absorbed by the calorimeter is first calculated using the temperature increase and the 374 J per degree C calibration factor. This energy is then set equal to the electric energy released by the heating coil to determine the time the 1.80 A current at 4.85 V was passed through the coil. The theoretical heat capacity of 100 G of water alone is 4.18 J per G per degree C times 100 G, meaning at least 418 J of energy should have been required to heat the water by 1 degree Celsius. Since the actual calibration factor was found to be only 374 J per degree C, which is less than 418 J per degree C, this leads to the conclusion that the actual mass of water present in the calorimeter must have been less than 100 G, specifically, less than 89.5 G. Scientific reality: the energy input was 374 J per degree, but the measured change of temperature was artificially low because significant heat was lost to the surroundings during the calibration. To determine the moles of sulfuric acid in excess, we must first calculate the amount of acid that was neutralized by the sodium hydroxide. Calculate neutralized moles using the stoichiometric ratio of 2 moles sodium hydroxide to 1 mole sulfuric acid. Calculate the moles of sulfuric acid consumed by the given amount of sodium hydroxide. Calculate excess moles. Subtract the calculated moles of sulfuric acid neutralized from the total initial moles of sulfuric acid to find the moles remaining in excess. Energy and fuel calculations. MCQ 1. Nutritional energy. The total energy available is determined by summing the specific energy contributions from protein, fat, and carbohydrates based on their content per 100 G. MCQ 4. Bioethanol efficiency. The actual mass of bioethanol required is calculated by dividing the theoretical mass by the given efficiency factor. Thermochemistry and kinetics. SAQ 2b. Exothermic combustion. The reaction is exothermic because the total energy absorbed during bond. Octane combustion. Stoichiometry. SAQ 2a. Complete combustion. The amount of carbon dioxide released is calculated using the mole ratio, stoichiometry, derived from the conservation of carbon atoms. SAQ 2c. Incomplete combustion. The insufficient fuel to oxygen ratio indicates that incomplete combustion occurs. Given that no pure carbon is produced, the sole additional product must be carbon monoxide. Excess reactant calculation. SAQ 5b. Excess reactant. The calculation involves 2 steps. 1. Determine the moles of sulfuric acid neutralized by sodium hydroxide using the 2:1 stoichiometric ratio. And 2. Subtract this consumed amount from the initial total moles of sulfuric acid to find the moles remaining in excess. Calorimeter calibration and technique. MCQ 29. Improving maximum determination. The inaccuracy in determining the true maximum temperature is due to the low frequency of recording, which allows the true peak to be missed before significant cooling begins. SAQ 5a.I. Calculating calibration time. The time is calculated by equating the energy absorbed by the calorimeter to the electrical energy supplied by the coil. SAQ 5a.2. Low CF justification. Because the measured calibration factor, CF, is less than the theoretical heat capacity of 100 G of water, the required test logic concludes the actual mass of water present must have been less than 100 G. The scientific reality is that this low CF is primarily caused by heat loss. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.